It's time to look at another operation, at another differential operator, this time working on the vector field, not the scalar field. And this operator is called the divergence. So let's look at the vector field in 3D first, which has three components, Vx, Vy, and Vz. And the divergence is defined as the scalar field made out of three terms. The first is the partial derivative of the first component with respect to x, second with respect to y, and third with respect to z. So first, notice that this is a scalar product, so that's a number which will depend on x and y and z, so it's a scalar value. And second, that it depends on the components of the vector field. So that's the main contrast with the gradient, which defined on the scalar field and gives a vector field. It's effectively somewhat an opposite example, where you have a vector field which is turned into the scalar field by applying the divergence to it. And we're going to learn more about what it is and why is it useful. Before we do this, let's also think about two dimensions. In two dimensions, you have only two components of the vector vector field, and therefore you only have two terms in the divergence. And you also can use the nabla operator, which we discussed a couple of times already, to define the divergence. You can see nabla written here with the dot in between, which is the same as the scalar product, and in fact it is exactly the same as in the scalar product. So it is nothing more or less than a scalar product between the nabla operator and the vector field, V. So let's take that nabla operator, which we considered in a previous video, and which you can also write in the sum notation like that. And if we take a scalar product of this nabla operator with the vector field, we will get the definition of divergence. So in fact, if we will get the vector field, which we also can write like that, Vx, Vy, Vz, and take their scalar product, then the divergence will be exactly as it's defined. So the second component and the third. So that is why it was useful to think about the nabla operator as a separate quantity, because now you can see that as we could introduce a scalar product for the vectors, likewise we can use the equivalent of scalar differential operator, scalar product of a differential operator with a vector field, to generate us a scalar field. But what does it mean? What is the meaning of divergence? It's actually not as straightforward as we have seen with the gradient, but we can discuss it anyway. And one helpful analogy is to think about flow of liquid, so fluid flow. And let's think about a small volume of that fluid, small element of that fluid, as it travels around and evolves. And what you can find is that when the divergence of this velocity field in the moving fluid is positive locally around in a small region, it means that this volume locally increases. So there is some net flux, so something generating that flow locally, so some source of flow. And that also corresponds to the increase in density. While negative divergence means that there is a flow towards this location, so effectively something is pumping out your fluid locally. And the density locally is decreasing. Well, as we talked about density, actually we can write this as an equation to predict a relationship between the density of the fluid and the velocity. And this is called a continuity equation, which describes how the rate of change in the density relates to the divergence of density times velocity field. And if density is constant, if the rho is constant, then this will result in disappearance of that term because it doesn't depend on time, and you will have that equation which is exactly telling you that divergence everywhere is zero. That means that there is no local change in density, which is a very powerful statement. And this equation itself shows you an example of the partial differential equation. And you can see now that vector calculus is critical to be able to formulate this equation. And the divergence is a very important concept. Then you talk about conserving some quantity.